All right. So at the end of chapter 9, we talked about a matched pairs t-test. Um, so on this next test, you're really going to have to be careful about a matched pairs t-test versus a two-sample t-test. These, like if you just glance at the data and don't really think about the data or how the data was collected, you could mix up these two tests. And these things are worth a lot of points. The hypothesis test is worth about 15 points on a test. If you mix these up and you'd run the wrong test, there's a good chance you're going to lose like 10-ish points. So you really want to make sure you are very careful to make sure you're running the right test. Students often get these tests mixed up. However, it should be easy to determine which test is appropriate by the design of the study. A paired t-test uses a matched pairs design, whereas a two-sample t-test is used on two independent samples. Matched paired test is a one-sample test. So you could just ask yourself, is it one sample or two? So let's just take a look at this. Determine which test should be run in the following situations. You're wondering if men at the John Cooper School are taller than women. You select an SRS of 30 girls and an SRS of 30 boys. The data is displayed below. Determine which inference procedure you would run and why. So I have two data sets. Two data lists, or whatever. Yeah, two data sets, I guess. Notice they're the same number. It looks like there's 30 in each. The question though is this guy and this girl paired? Are they linked in some way? And this is just a simple random sample of guys and a separate simple random sample of girls. So there's no pairing between these two data points. I could change the order of this female list and it wouldn't matter at all, right? In fact, I could have more females on this list, right? They don't even have to have the same length. These are two independent samples, so it's not paired. So I need to run a two-sample t-test for the difference in means. Okay? So here's the data set. Looks like there's going to be a difference here. This mean is like here, this mean is here. There's a pretty good separation. Looks like this is going to be a significant difference. Here's the output on a calculator. Test statistic 8.7, p-value very small, 0.0011 zeros and a 17. Degrees of freedom, 57.9956. Yeah, you can see all the stuff. I do want to take this time to just expose you guys to computer output. This is from Minitab, I believe. It's the software I use, so when I do computer output, it's going to look like this because it's from Minitab. So this is a two-sample T for males versus females. So here's the summary information. This is the mean of the girls, the standard deviation of the girls. This is the standard error of the girls. And same with the guys. So we're doing a difference, mu of males minus mu of females. Estimate for the difference is 6.36. That is the actual difference in my two means. 6.36. Lower bound, 95% lower bound for the difference. This is actually a one-sided confidence interval. Let's just not even worry about that. And then here's the good stuff. A t-test for the difference. The null is equal to 0 versus greater than 0. There's the alternate. So they kind of condense it all in here. There's the null, there's the alternate. Test statistic, p-value, degrees of freedom. Our calculator certainly has more precision than this computer output, but whatever, doesn't matter. So if I give you this, you should be able to get the information you need off of it. Okay? Example 2. You're wondering if the male and a brother-sister twin pair are taller than the female twin. You randomly select 30 sets of twins and record the heights of both siblings. The data is displayed below. Which inference procedure should you run and why? So here's my brother list, here's my sister list. It looks like two samples, right? Two lists, but it's not. This is paired data. This brother-sister pair needs to be linked together. I could not, for example, just change the order, like sort the sisters from short to tall, because I'd lose my pairing with the boys, right? So this is paired data. I could not have more girls than I have boys. Another way to look at it is I took a single sample of 30 pairs. This doesn't look like 30. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks like it's just 10 sets. But it's a single sample though. This isn't two independent samples. So you should not be running a two-sample t-test. In fact, you shouldn't even really be looking at this data like this. Here's the heights of the girls, here's the heights of the boys. Looks like the boys are maybe a little bit taller, but it's like if I was just looking at this graph, I would say that's not a significant difference. But this graph isn't taking into account the pairing. The fact that the tall brother has got a tall sister because of genetics, and the short brother has got a short sister. This has got all that variability in all the different heights. The reason we do a matched pairs design is to reduce that variability. So if you run the wrong test, you get a test statistic of 0.9 and a p-value of 0.189, and you would fail to reject. So not enough evidence, right? But that's not what we should do. What we need to do is we need to take a look at the difference list. What are the differences between the brothers and the sisters? We should do a one sample test on the difference list. mu-d, right? Average difference. So here's the differences. I'm wondering if these differences are significantly greater than 0. And it kind of looks like the average is pretty much higher than 0. There's a few that are lower than 0, but most of them are higher. It looks like the average is around here somewhere. If I run a one sample test on the differences, or a paired t-test, I get a test statistic of 2.76. I get a p-value of 0.011, and I reject the null. So I just want to point out what happens here. There is a difference, okay? You do a two sample test, you don't see the difference. You don't have enough power. There is a difference, but the probability of rejected is too low. Down here, we rejected it. Power is the probability that you correctly reject when there is a difference. Here, I correctly rejected when I had a difference. What a matched pairs design does is it eliminates all of this variability here, and it gives us a more powerful test that allows us to reject more often when there is a difference. So matched pairs design is a very nice design. Okay. Oh geez, last example, testing with distraction. Okay, let's just do this real quick here. Suppose you are designing an experiment to determine if students perform better on tests when there are no distractions, such as a teacher talking on their phone. You have access to 2 classrooms and 30 volunteers who are willing to participate in your experiment. A, design an experiment so that a 2-sample t-test would be appropriate. Okay, I'm not going to write all this down, but if you wanted to do a 2-sample t-test, you would randomly divide those 30 kids into 2 groups of 15. You would administer the treatment. In this classroom, you'd have no distraction. In this classroom, you'd have yes distraction. You would calculate their scores in both, on the same test, and then you would compare those scores using a 2-sample t-test for mu1 minus mu2. Problem here is there's going to be a lot of variability in these 15 kids. Some kids are going to be good, better, smarter kids, I guess, and some kids are going to, not be, sounds kind of harsh, but you know what I'm saying, right? A lot of variability. This test doesn't really account for that variability. So that variability is going to work against the chances that we get a significant difference here. B, how would you do a paired t-test? Well, I'd take my 30 kids and I'd give every kid a test with distraction and a test without. I still have to do random assignment though. So what I would do is I would take 15 and I'd give 15, randomly give 15 the test. So these ones I'm going to give the with distraction test first. These 15 I'm going to give the without distraction test first in each of my 2 classrooms, right? Then I'm going to have them switch classrooms, or I'm going to give them the without distraction test. Now I might have to talk about how to do these tests, so that maybe, we don't want them to be the same. We don't want them to be able to, you don't want the first test to help them with the second test, but the fact that that half of them randomly did one first and the other one first kind of is going to account for that, at least a little bit. And then I'm going to do a paired t-test. I'm going to look at the difference in these two. This is going to have more power because I'm not comparing Johnny's test grade to Susie's test grade. I'm comparing Johnny's test with distraction to Johnny's test without distraction. So, nobody's more like Johnny than Johnny. So you're reducing a lot of that variability. This should give you a more powerful test. Which experimental design is better? Paired, for the same reasons I've been talking about. All right. And that concludes chapter 10.